Hello, everybody. Welcome back to Mankind in Training. I am your host, Joshua Parr. I have another quick, well, not quick. They've been pretty long lately, but I'll try to make this one quicker if possible. I have some demonstrations. We're gonna run through some functionality in the Wolfram Alpha notebooks, and I'm also the very first thing I'm gonna do is I've been showing quantum circuit operators in the last couple of videos, and I made a little diagram. I kind of want to explain what's going on a little bit with that. So, without any further ado, this is the Wolfram notebook. Put me up here. All right. So, this is a little, it's sloppy, I know, a quantum circuit I drew up. So, this is kind of how these go. So over here, I have these ket states. It's a qubit. Qubit alpha, qubit beta, qubit sigma minus, qubit sigma plus. And they run through the circuit one directionally. You start out with one qubit here, you get one qubit here. Now, each of the qubits also has, so this circuit has an analog where it'll have the actual electronical 0-1 coupling circuit with each one of these. So in this particular diagram, what it is happening is there's 4 qubits being operated on, and then the two 0 and 1 normal circuits. So right here, this is a representation of a unitary random gate on alpha and beta, and another random unitary on sigma plus, which is so 1, 3, and 4. And then the next, so you might as well think of these as a time sequence, even though it's in the hypergraph simulation, it may not necessarily update everything. It will when you specify for it to, but it can update things in any which way it would like. But when you actually run them through a quantum circuit, it is when you actually measure a real quantum circuit on a real quantum computer, this is what's actually happening. So I'm sending the qubits through. I got a unitary, and nothing happened. So you might as well call it just the identity. Nothing happened. I have a Hadamard here. And then I have a controlled NOT gate here. And then I have a swap from 1 to 4. And then I have, this is the beginning of, I tried to draw kind of like what the Fourier transform does. We have controlled gates, the e to the half gate, the e to the quarter gate, e to the eighth gate, but I have them arranged in an odd fashion, and I have a double FFT on 3 and 4 down the time sequence here. And then stopping, we now have an X gate, a rotation of theta on the X gate, and oh yeah, I was supposed to draw lines through here. Whoop. So that was supposed to go there. That's supposed to go there. And now I am doing a controlled X on 4 and 2. And then I have a controlled NOT gate on 3 and 2. And then this actually should be also connected to 8. And then this e to the quarter was supposed to run up to there. Whoops. So we have these series of gates, and now I have an uncurry gate controlled, or maybe we should just go controlled U. That's what I call that for now. And then I have not, and a control on, and then another random unitary. And then I have 3 measurement gates on 1, 2, and 3. And then on the outside, you get the measurement of alpha, you should get a measurement of beta, and we should get a measurement of sigma plus. And that is kind of how these work. Go back over to the Wolfram. I'm covered by a math input. So here we are. A little bit of functionality in the Wolfram notebook. So firstly, I did right here is you can see, how do I do this here? All right, so do something similar just to show. You just type in, oh, no, I do need to, whoops. There we go. This should work now. All right, if you press equals and you get the orange button, you can literally type in plain English most of the time and it will figure out what you're trying to do. Sine 5x to the y as x approaches r pi y and it solved it for me, gave me my limit. And it did the same here when I asked for x cubed plus 2x times 2 minus 8 as x approaches -5, limit 150, -153. And then I did the same here as 3x squared, x approaches 2 pi r. I got sine 12 pi squared r squared. And then for this last one I asked for, we get a beautiful cosine 5 pi to the negative y, ry to the negative y. Now, say I got my answer here. So look right here. I can plot this. And it was just easy peasy right on the button. And I can plot that function as it approaches. And it's an asymptotic looking function over here. Or say I want, okay, we're back here again. So I want the y integral of this. Bam. Say I want the x integral of that. Oh, what happened there? Oh. There we go. So I asked for it. The options come right at the bottom, nice and easy. It's very intuitive, very easy to use language. I'm such a fan of this. I could just play with it all day. It solves all of your problems. It really does. There's a little bit of slowness and there's some things with Packlets that, but like the overall knowledge that you need to have before starting is next to none. It's very, very easy to use. You don't need to be an expert in any packages of any kind. And a lot of the commands are what you'd expect the command to be. I really like this language a lot. So here, I asked for, yep, we got, that was from answers from up above. We got partial derivative, and we got an integral for r. Here I'm asking for x squared minus n over the gamma function of 3 minus n minus delta sub n k omega minus t theta of q. And I'm asking to make n h over root negative sigma I times 2. My answer gave me the answer. We got x to the 2 minus h over 2 times the negative root sigma I over the gamma function 3 minus the h over 2 root negative sigma I minus q k omega minus t theta delta and then again. And then I asked for the integral of t, and it gave it to me. And then I asked for the partial derivative of t, and it gave it to me. And the answers were right there. So that's nifty. Let's do that. Do a contour plot. Maybe it doesn't like that. Whoa. All right, so how about not a contour plot? Let's go a density. Will you do that for me? No, it doesn't really want to do that either. Most of the time, if your function isn't outrageous, it can find a common what's going on here? Well, usually when it has the answers built into the bottom like that, it usually means that it has something that it will display for you. I'm not entirely sure why that didn't work. So hopping down, it's probably because of how gnarly it is. Just more examples of when I asked for specific things and it kept breaking them down. Partial derivative t again, and then partial derivative theta. So here's a fractional derivative function, and I'm taking the fractional derivative of the exponential function x cubed t alpha squared plus xt root negative I over yz minus k times alpha x beta t cosine epsilon k minus sine omega t for x and alpha. And it did a full solution set. It's even got ceilings, difference roots, solves for alpha and x. Get everything over beta t, get alpha x cosine, epsilon k minus sine omega t. So I doing another fractional derivative here, simpler one of x squared divided by 2 for x and alpha again. And this time I got x to the 2 minus alpha and then the gamma function of 3 minus alpha. So I'm asking for a Capito and then a Bessel function, 1/3 in x and then x and 1/2. And you get root pi hypergeometric PFQ. And then we get 2/3, 7/6, 5/12, 11/12, 4/3, and then negative x squared over 4. All over 2 to the 6th, x to the 6th, gamma, 5/12, and gamma 11 of 12. And then I'm asking again for another fractional derivative, this time of the Bessel function, nu and x alpha. Does it for you. It does it for you pretty quickly too. I'm asking for it to just solve x squared plus a times x plus 1 equals 0 for x. So I just edited some things just to show you that you can put whatever you want in here and it will figure it out. It will absolutely figure it out. It really does. It'll figure it all out. It'll do it quick, fast. That is just incredible. So this time I'm solving again. I'm asking for the real numbers. Only real numbers. Only real values. Now nsolve is numerical solve. So you get an actual number. You usually get a float of some kind for accuracy. There's some imaginary characters in there. And you can convert them into arrays and vectors. And so asymp solve is a different one, asymptotic solve. Here's a formula I gave it. And 3 parameters at the end for y. And I get exactly what I asked for. So here, this is another nifty thing. I asked it for Planck's radiation law and the wavelength, and to formulate, or in the formula data for its frequency, Planck's radiation frequency, and it set it up just like so. L lambda and L nu. This is an abs argument plot. So I asked for sine I of x, sine pi of x, yada, 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 and give me an abs arg plot. And here are the expressions. Expression 1. Oh, that's expression 1. That's expression 2. And they're plotted against each other. Here's another one. It's the fill of this same thing minus that line there. Same exact parameters. So here is something. This is an array plot. Now, if you've seen when I was making quantum states, quantum operators and things, this is how they kind of pop up. The Wolfram language turns them into an array that has a heat map to it of what, depending on what you're doing, it'll have different colors for what you're doing, and for what the operator is and what its value is. But they've been showing up. I kind of like this idea where they are making a heat map of an array and you're getting a visual representation of what that looks like, and then what happens when you flip bits, and what happens when you do a swap, or what happens when you do root I or root X or rotation Y. Here's another array plot with a heat map to it. Same type of deal. If you remember, you'll from any of the other presentations from before, a lot of the quantum operators, like I was saying, look something like this, This one is, instead of them all being the same size, it chooses at random size. And these are good ways to set up like good random, you can build a quantum state out of these, actually, and turn one of these into a quantum state. Here's one that I know is a quantum state already. It's there's a Schrodinger measurement that looks just like that, different colored, but. And then here is another Schrodinger vector that is very, very similar. This is just an array plot with a heat map, but what I'm saying is that there are dimensional projection operators and measurement operators that look a whole lot like this. The computer, in fundamental nature world, Wolfram's on it, man. He's got the hypergraph system, and the hypergraph is dimension is not a thing anymore because the computer is understanding dimensionality better than we ever could have imagined. The fact that we have all of these degrees of freedom, and you might as well just think of everything as quantum basis states and quantum operators. Literally everything in the universe can be broken down to those things. They're quantum states and quantum operators that build the classical world that you live in. And there is a underlying the Wolfram framework, there is a tensor network that can be directionalized, that can be amplified in dimension, that can be lowered in dimension, that can be projected onto different dimensions. It's absolutely incredible. And we're starting to learn that maybe the world is kind of more computational than we would like to have thought. So here's another functionality. It's called a slice vector plot. And I've given it the parameters. And then I have walls in the center of my cube, and then showing the vector relations by spot. Now that right there can be turned into a circular, what's the embedding, a circular embedding, and you can make one of these out of it, and then you can make a quantum circuit out of it. You make a quantum circuit operator, a random graph quantum circuit operator to measure, or if you need to, what's the word I'm looking for? You need to closely approximate a certain system, and the best way to do so is to feed directionalities just how you would expect the system to behave. This might be your best bet to how to go about doing that. So so this is saying 1 to 2, 2 to 3, 3 to 4, 4 to 1, and 2 to 4. Now what if I do this? There we are. And then what if I do that? There we go. You can literally create them any which way you would like. And then let's say 3 then points at 5. And you can make these circuits any which way you like. You can put the directionality. You can make them so they're not, so they're just connected and one's not directed at the other. So here's a series of graphs This is a generalized this is the edge rules. No, yeah. No, yeah, we're using edge rules from above. This is a Peterson graph, this is the Clebsch graph, and that's the tesseract graph. Now, this tesseract graph is actually incredibly important. You can pretty much use all of these as measurement operators and graphs of the tensor network, and all of them are incredibly important because they all end up when the tensors do build out, they usually form in ways that make sense. So here's another graph plot. And this is so if I have a huge, densely connected network and I want to sample connectivity from various points in the network, I could take random samples just like this and then return their associations. And that would teach me a lot about what's going on behind the scenes. So here we go is a Peterson graph, layered graph plot. Another layered graph plot where I specified the directionalities. And I specified that I wanted it to be a left Ah, yeah, that's right. There we go. What's going on? All right. And I changed what was there just initially. Say if I want the right decomposition. Get right decomposition. There we are. Here we are. This is bipartite embedding. It's a good way to cross sample. Real quick bipartite. So here I have this Wolfram can do everything. We have neural nets now. We have neural networks and artificial intelligence, predictive algorithms and models. So right here, I'm creating a variable called net, and it is a net graph, linear layer, net port, and this net graph object works like so. And now I'm initializing that net object. It's got vector size 2 and an output port size of 2 as well. Input and output port size, same as before. Now it's initialized. Now I'm taking inet and feeding in 2 values and getting 2 results. Creating another variable called chain. And I'm net chaining the ramp and logistic sigmoid at 1 and 2. And now I'm creating net graph of the chain I just created. And it looks a little something like this. Now I'm creating a sparse array with various connectivities. Now I'm creating a classifier function for logistic regression. And now I am asking for the measurement of that classifier. I get a logistic regression with 4 samples. It got 3 out of 5 of them correct. Or it got 3 out of 4 of them correct. The accuracy baseline is 50 plus or minus 29. Geometric mean of probabilities 0.344. The cross entropy is 1.07. Batch evaluation speed did 302 examples in 3.42 milliseconds. And this is what are them called? Why am I drawing a blank on this? A confusion matrix? Confusion density matrix? Something like that. And now I'm creating another test set and classifying the measurement of test set C, and I'm asking for its accuracy. And again, it stated it already there, but I'd ask again to show you that you can. And then I'm asking for error, the accuracy, the error, and the mean cross entropy. And you get it all in the same answer there. Easy way to do that there is this accuracy. And you can compute the uncertainty of the accuracy. Another classifier measurement, straight up. And then here are some more specifications. And then I'm asking for the cross entropy now after those specs. And again, got the same value both times, so there's confidence is the same on either side of that. So creating another net chain object. It's not yet been initialized, but I'm stating that it's a softmax layer and it's a net decoder for classes A and B. And now I'm giving it more A and B values, net chain. And then now we're going to do some measurements. Training for accuracy, still 75, and confusion matrix plot. Now I'm creating a predictor function again. Linear regression for 4. And a new test set. And I'm asking for the measurements standard deviation. We got 1.8882. Here's a residual plot. So this is the baseline. These are your data points, and the residual is the distance from 0 in either direction. Predictor measurements, comparison plot. It's actual values, predicted values. Here's another predictor measurement set, asking for SD, R squared, and mean cross entropy. I'm creating another predictor function. This one's numerical, though. Instead of regression, it's going to be a decision tree, because I'm building a neural network to make some decisions. Here's, I'm creating some predictor measurements. I'm doing some predictor measurements on that decision tree. There was 3 examples, standard deviation of 2.19, baseline 1.55, R squared negative 101, mean cross entropy 2.30, single evaluation time 3.44 milliseconds per example, 185 examples. Batch evaluation speed. So got standard deviation, uncertainty computed for both, and the R squared. Got predictor measurements, standard deviation, and then we got another predictor measurement. Keep sampling them. I'm asking for the log likelihood of normal distribution. So now I'm training a model here, the LeNet, for the fashion MNIST dataset, and I'm asking it for its accuracy. It did 938 batches, 1 round, in 1.5 minutes, 678 examples per second. Training examples, 60,000 processed. 60,032 skipped examples. We used the atom optimizer, batch size of 64, and our loss was 4.54 times 10 to the negative 1 with an accuracy of 83.7%. I thought this is nifty. This is such an amazing language. It really is. So, oh man, there's so much more still. All right. I really didn't mean for it to be this long again. So, S equals an ND solve. I'm getting a Hermitian scalar output. I'm plotting X of S, Y of X of S. And now here's the parametric plot showing Y of X and Y prime of X of S. And then I'm asking for a specific value in this plot here of Y and Y prime to return the value of S at Y and at Y prime. And it does. It's so amazing. It does literally whatever you want. Anything you want done, it will do for you. Doing it again. This time I got a different scalar output than before because I've changed the equation. Now I'm plotting Y of X, Y prime of X, Y double prime of X. Triple function. Differential. Okay. So again, doing a different one. Interpolating function of X. Got two outputs here. And I'm parametric plot of that. Another ND solve. Give me a U interpolation. Here is that same U interpolation, but a 3D plot of it. It's like the saddle, little offset. Here's another situation where I'm ND solving for a U interpolation, getting scalar output, 3 to 5 order. And then I'm doing another one with a Laplacian of U, X, and Y, and a Dirichlet boundary condition of U, X, and Y equals 0 for U, X, and Y in the disk that I created. It says it's unstructured, but here, and I have the bowl. So I have it. What's going on here? There we go. Here we go. Interactive gradient, and I'm applying that to del X and Y. Del of X and the curl, if you will. X and Y, the curl of X and Y of the disk. And then here I'm doing another one. It got pretty complicated here. I was trying to get as fancy as I could. ND solve, and it's got the Laplacian function, the Dirichlet condition function, the ND solve function, the polygon function. I could probably wrap it in it's got a sine function. I could probably wrap it in an exponential function just to show you that you can do everything. Literally do all of it. There's no bounds. You might find that there's issues with how you formatted it, but other than that, everything is beautiful and works exactly how it is supposed to. And then I'm here plotting these parametric regions as that function changes 3 dimensions. So here I'm ND eigensystem of the Laplacian U of X, U of X. A pi, 0 to pi, scalar, 0 to pi, 0 to pi, 0 to pi. Interpolating functions. That one's a second order. That one's a second order. Second order. Gave me the answers I was looking for. 1, 2, 3. 1, 2, 3. For 4 of them. 1, 2, 3. I want to flatten that. It gave me the option to flatten it, but it didn't actually do anything. So, back to here. So I plotted this eigensystem that I just made up there. Evaluation of it over 2% of time. Now I'm creating a random real convex Hall mesh. Looks a little something like this. To be some polygon that's fully connected. Convex hull. And integrate x squared, y squared, z squared for x, y, and z in the elements of this convex hull. And that is the n integral. Scientific form. Another n integrate function, 1 over cosine x log of x divided by x, x0 and 1. Get my answer, and then I plotted my answer with cosine log of x over 15. Now I'm doing some combining here, making a plot of the Airy function and the Bessel function. Bessel J, Airy AI. And then here is a plot representation of the information and integration. Again, table. This is a measurement of this function over time, and it's being projected into the complex vector space. And integrate. Got some more Bessels, Bessel K, Bessel I, Airy AI, Airy BI. Triangle wave. I created the triangle wave, the bounds for it, and then I'm plotting the triangle wave that I created. Asymptotic value, desolve value, y prime of x equals 3z of x, z prime of x, y of x, z of x, x1 and 3. Bam. Does it. Quick, fast, hurry. All right. And then this, at the end here, I just had a couple of, I'll show you what I was talking about. And there's a my pure state Schrodinger vector, quantum state 1, 2, 3, 4 for Wagner. The Wagner associations look like this: W naught naught. And these are the amplitudes. And there's amplitudes. So here's Deutsch. The Deutsch operator. Let's go with, I want the associations here. There we go. I was about to say, it might have froze me up because it's a very large dimensional object, but we've got a series of sparse arrays, just what I was looking for. These are the associations of this operator. So go with this. / matrix form. There we go. Show you a little what's going on. These are the amplitudes for the Deutsch algorithm, or the Deutsch operator. Normal quantum state there. All right, so here we go. Hmm. Yeah, what was I trying to do again? Yeah, it's not gonna do that. Ah! Good enough. Just to show. I'm getting ready to wrap it up here. I just was trying to show you a couple of things if I could. There we go. This is a quantum channel. It's rectangular because it's only going to operate on part of this. So let's go just show you what. Whoops. Whoops, 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 whoops. But it doesn't stop. You can do literally everything. You can do whatever you want. Really? There we go. And so I think that's kind of all I wanted to show extra today. Oh yeah, I was gonna do a quantum partial trace. Well, I will make a whole. I'm gonna do a whole thing about that one. So I think we're gonna cut her off here. Um, quantum basis computational. Look just like. Come on. Go. Yeah. Let's see if this lets me do it. Probably not. Yeah. Yeah. I can do it. It's just difficult. Anyway, yeah, I should probably stop there. I was just trying to show some functionality of what you can do. No, it doesn't want to do that. There we go. Thank you everybody for watching. It's been there we go. That's actually what I was trying to do. Okay. I think I may have figured it though. Thank you everybody for watching though. I going to make another presentation, that is for certain, because I can't get enough of this. I'm going to just keep showing as much of it as humanly possible. So you guys have a nice day. I hope to see you back in the next installment of Mankind in Training with me, your host, Joshua Park.